Konnichiwa, Zamurai Engineer desu. In this continuation module on the evaluation of the step size effect on the accuracy of our approximation to first derivative, and the method that we're going to use is central divided difference. So we would like to know the characteristic of the result if we change the value of the finite, the delta x. Okay, so what would be the result? What will happen? Okay, so let us proceed. But now, since I already explained how to solve for the true error and also for the absolute relative true error, at the same time I was also able to explain and give an actual problem solving example in finding out approximate error and also absolute relative approximate error. So therefore, in this example, we will focus on the significant digits. Okay, so in solving significant digits, we will actually use the approximate error or the absolute relative approximate error. So we will set a criterion which, if I would remind you, is equal to the criterion or the epsilon s is equal to 0.5 times 10 raised to the exponent 2 minus m, where m is the significant digit. Okay, so that's how we would like it to be. So our unknown here is the significant digits, the m. So we will what? Solve for absolute relative approximate error, then equate it to 0.5 times 10 raised to the power of 2 minus m. And therefore, one equation, one unknown, we can solve for the value of m. That is the significant digit. Okay? It's very simple. Or, instead of doing that, the simpler style, the simpler technique is, we know the absolute relative approximate error given in this fourth column here. This is the fourth column. You already know this. And this value should be less than or equal to whatever the value that will be solved in the expression 0.5 times 10 raised to the quantity 2 minus m. Okay, and therefore, what will happen? We will just try 1, 2, because the value of m must be integer. That's why that is the simpler style to solve this, because the value of m is integer. Because m is what? Significant digit. There is no significant digit that is equal to 1.5 or 1.4. Significant digits 1, 2, 3, 4. First significant digit, second significant digit, third, so on. There is no 1.5 or 1.75. There's no such thing, significant digit. So because of that, it is simpler to what? To evaluate the criterion and compare it to the value of absolute relative approximate error by using integer on the value of m. M is the significant digit. Okay, let's go. So we have an function given, we have still the initial value for delta x is 0.05. Still, we have the value of x as 0.2, and we are being asked to solve for the first derivative using central divided difference. We can do that. So how to do that? The first derivative is equal to fx plus delta x minus fx minus delta x divided by 2 delta x. That is the approximation, the central divided difference method. And the actual value is still the same. The actual value is here, which is 80.119 or 80.12. So I will just solve this one, the significant digits, to show you how to solve this. Let us screenshot this table and try to prepare ball pen, paper, and calculator. So please let us show you the calculator. Let us proceed. So we have the calculator right now. So we have what? We have the criterion expression. What is the criterion? 0.5 times 10 raised to the power what? 2 minus m. M, we have m here, right? So we have m. So therefore, what will happen? So let us start with 1, right? Let us start with 1. M is 1. So let us start with 1. Okay. So this is the criterion. This is the criterion. Take note, 1 is the value of m. So m is the variable that we would like to know. So on the first line of the table, we don't have any answer because there is no previous approximation. That's why we cannot provide an answer for approximate error, because approximate error is present approximation minus previous approximation. There is no previous, so we cannot solve. Let us go directly to the second line of the table. Okay. Second line of the table, we have what? 0.500417 as the value of absolute relative approximate error in terms of percent. Okay. And because of that, we can evaluate this this expression and compare if this expression is greater. Must be greater. This must be greater or at least equal. This cannot be less than. Okay, so let us find out. If this is greater than 0.500417, it is equal to 5. Okay? It's equal to 5. Therefore, it is not greater. It is not greater. So therefore, m should be 0. So let us replace this by m is equal to 0. And the answer would be 5. The answer is 5. 50. Huh? Answer is 50. Let us go back. Let us replace this by 1 and equal sign 5%. So 5% is correct because 5% is greater than 0.500417%. Of course, 5% is greater than 0.5. Okay, because as you can see from the table, the first number there is what? 0.500417. 0.6 is greater than that because that is 0.5. 0.6 is greater than that. And 0.6 is less than this. So this is 5 is greater than 0.6. And therefore, it satisfies the criteria. It satisfies. Okay, so it is enough. Therefore, m is equal to 1. So this value of m is correct 1. So there is only one significant digit that we are sure to be correct. We are sure to be correct of one significant digit. Okay, and therefore we are not satisfied with that because we have only one significant digit. Meaning, if our answer is 80.25307, we are only sure of the value of 8. We are not sure of the value next to 8, which is 0 in this case. No? We are very sure of 8. Okay, let us be sure of the next bar. By what? Putting here the next line, the third line. The third line, let us put here 2. What will happen? We 0.5. This is 0.5. Third line, 0.5 is actually greater than point. Take note, on the table, third line, on the column, the fourth column, you can read fourth column is 0.125026. Okay, that is the absolute relative approximate error. The value there is 0.125026. And that is less than this value 0.5. And therefore, 2 is correct. Because this 0.5 must be greater than the absolute relative approximate error. Okay. So let us again go to the fourth line. Fourth line, we have absolute relative approximate value, which is equal to 0.031252. So let us use 3. Okay, significant digit, 3 significant digits. Okay, let us find out if we have 3 significant digits. 1/20. 1/20 is what? 0.05. 1/20 is 0.05. Is it greater? If it is greater, it is correct. Yes, it is greater because 0.05, this one, is greater than the amount in the table, which is 0.03. So 0.05 is greater than 0.03. That's good. Therefore, at the fourth line, our answer is sure to have 3 significant digits because our answer is m is equal to 3. Therefore, we are sure that the 3 significant digits are correct. What are those? 8, 0, and 1. That is what? 80.1. We are sure with the number 80.1. We don't know the next number. The next number on that line is what? 2. Okay, 80.12. We are not yet sure of that fourth significant digit. But the 3 significant digits, 8, 0, and 1, we are sure that is 80.1. We are sure about that number. And actually, if you can, we already know the answer. We already know the answer. The answer is 80.119. The answer is 80.119. And that is correct. We are sure with 80.1. That 3 significant digits we are sure. Okay, I already shown to you the technique how to solve this table using different methods, 3 methods, and the rest you have to complete the table as your practice, and you can use those practice problem solving to be your comment on our videos for your attendance. Okay, well, let us go back to our PowerPoint. So let us give you the opportunity to practice and complete all of the values here inside the table. Okay. So effect, what is the effect of step size? How can we do this? Tabulate the values that we calculated. So we calculated almost the same value, 80 point something. From the start, you already calculated 80 point something. But still, we are going nearer and nearer to the true value. Okay, so effect of step size on approximate error. You will notice always the first few approximation very big error, but after that almost zero error. So if you can see from all of the example, forward divided difference, backward divided difference, and central divided difference, about three, about the fourth line or fifth line, 4 or 5th line is sufficient. No need to go to this length, no? 1, 2, 3, 4, 5. The 5th line is enough. No need to go to this length. Okay, almost zero, almost negligible. So this okay, 1, 2, 3, 4, 5. The fifth approximation is almost acceptable. It's already acceptable. Even the fourth one, but we want to be precise, but no need to go to this length. Okay. So it depends upon the application. Depends upon that. There are applications that we really need to go up to the 10 or even 11. Okay. So it depends. This is the effect of step size on absolute relative approximate error. Okay, and the number of significant digits. So we are able to number of steps involved. Okay. Least number of significant digits. We already know. Number of steps involved. 2 steps, 3 steps, 4 steps. Yeah. Okay. So effect of step size on the true error. So we have 1, 2, 3, 4, 5. So the fifth one is really here, even the absolute relative true error. 1, 2, 3, 4, 5. The fifth one. So is already acceptable. So this is how we gain an experience and insight. How do you know that the fifth one is okay? If you have an experience. You cannot do it if we don't have the practice in real problem solving. You cannot say it. You cannot say that. Would you do the repetition up to 11 like this, up to 11? No. You have to do up to 5 or 6. Even 4 is already. So it depends on you. What kind of engineer are you? Okay. Are you an industrious engineer? Okay. Do you have time? You have time to repeat and repeat up to 11. It depends. Do you want to be known, to be precise? Do you want to gain a name for yourself that everyone will call you the Mr. Precision Engineer? Okay. Okay. It depends. It depends on individual. So, but if you are not so industrious, maybe you will use this. It's okay, but the error is too much. Maybe you can use this. Okay, you can use that, but the error is too much. Okay, and so. And because of that, we gain a very practical insight on how we should decide. There is no guesswork. We did not guess. We can be sure how many significant digits are 100% sure to be correct. We know. Even if we are just doing the approximation, we have an idea how many significant digits we are sure to be correct. Sure in terms of mathematics means 100%. We are 100% sure that the third significant digit on our example a while ago is 100% correct. That is the 8, 0, and 0.1. We are very sure of that. And we showed to you that that is true. So that is the beauty of numerical method. We don't need to use calculus. We don't need to use calculus. We did not use calculus. We just approximate it. Okay? We did not use calculus. But the level of accuracy is there. Level of accuracy is here. What is the difference between this 0.6 and 0.7? They are almost zero. They are almost zero. They are almost zero. They are almost on the zero line. Okay? You use calculus, you will get the correct answer. However, I did not use calculus. I use numerical method because of practicality, practical application, engineering. But still, my answer is almost the same as you. Okay? While you are using them. Okay? All of the mathematics from your first year and second year, we can approximate by numerical method to a level that we accept as a sure correct answer. Correct answer. If the answer is good for 3 significant digits, for example, a mathematics teacher could say, okay, class, please solve the value up to 3 significant digits. We can be sure. Use numerical methods and find the answer up to 80.1. That is the 3 significant digits. We are sure. Without doing the calculus. We just did the calculus on the example just to show you and to calculate the actual or the true value. Just to calculate the true value. But aside from that, in the real world, we don't need to know the true value. We don't need to know the true value. We are sure to compute the significant digits. If we are looking for what? Measurement. 1 decimal point is enough. So 80.1 is enough. If you are using the tape measure, 80.1 is already sufficient accuracy. You cannot measure 80.11. You cannot measure it in your tape measure. Or if you can, it's very hard. It doesn't matter. It will not matter. It will not matter in real world. In engineering, it doesn't matter. It will not matter in real world. If my unit of measure, for example, my unit of measure 80.1 mm. Okay, measure it. 80.1 mm. Measure it. Use your ruler and compare it to 80.12 mm. Okay. I will get your paper. Put down in your paper. Measure 80.1 mm. 80.1 mm, and also another one 80.12 mm. So take note of the difference. What is the difference between the two? Take note. In actual. what will you do as an assignment? Cut a paper using your scissor, measure 80.1 mm and cut the paper. This is the paper, length of the paper. And cut another paper which with length 80.12 mm and show me next time. Next time we have the live lecture, I will ask for it. Show me the difference between 80.1 and 80.12 mm. And you will surely experience what I'm talking about. That engineering is different from mathematics. Okay? So anyway, that's all for this module. Thank you for listening. Again, this is Dr. DrEYPEI, preaching engineering for nation building.